We tend to look at the history of life on Earth like a blockbuster movie franchise, where the dinosaurs were the perfect first film. They had the size, the teeth, and a 100-million-year run that ended when the asteroid hit. In reality, the 66 million years that followed, the Cenozoic era, are where the plot becomes incredibly complicated. The planet's stage underwent a period of physical demolition and reconstruction. The KPG extinction event wiped out the non-avian dinosaurs, the pterosaurs, and the massive marine reptiles. This created an ecological vacuum, a bustling world where the consumers, the movers, and the apex predators vanished overnight, leaving the food web in a state of collapse. Surviving life responded to this void with extreme aggression. In North America, the number of mammal species doubled within 100,000 years as life rushed to fill the empty hierarchy. The mammals that survived the asteroid were small, nocturnal creatures. Yet their body mass tripled in just 300,000 years. This rapid growth requires immense fuel, but the post-apocalyptic landscape offered little more than low-calorie ferns and scrub. The fossil record shows a solution appearing 700,000 years after the impact, the legume family. These plants evolved a relationship with bacteria in their roots that allowed them to fix nitrogen directly from the air, creating a built-in fertilizer factory that packed seeds and leaves with protein. These high-density botanical energy drinks provided the nutritional raw material for mammals to grow. With more protein available per bite, surviving lineages could specialize and rapidly scale up to conquer the land. 56 million years ago, the planet experienced a massive global warming event called the PETM. Forensic analysis of carbon isotopes points to a methane burp, the destabilization of frozen gas on the ocean floor, which injected over 2,000 gigatons of carbon into the atmosphere. Global temperatures rose 5 to 8 degrees, creating tropical dead zones, while crocodiles inhabited the Arctic. Acidic oceans dissolved seafloor shells. Mammals adapted via the Lilycrit effect. Early horses shrank 30%, coping with low-calorie, high-sugar plants. This shift in the fossil record suggests a link between the atmosphere's chemistry and the physical dimensions of the animals forced to survive within it. The Earth's cooling was driven by the movement of the continents. Roughly 50 million years ago, the Indian plate began a slow-motion collision with Asia, pushing up the Himalayas and the Tibetan Plateau. These mountains acted as a thermostat. Rain absorbed CO2, became acidic, and reacted with rock, scrubbing carbon from the air. Washed into the sea, marine life built shells, forming limestone layers that bears atmospheric carbon for millions of years. A second tectonic shift occurred at the bottom of the world. Antarctica physically separated from South America and Australia, opening new ocean gateways. This allowed the Antarctic Circumpolar Current to form, an uninterrupted loop of water that thermally isolated the continent. This current acted as a barrier, preventing warm tropical water from reaching the pole and locking Antarctica into a deep freeze. The movement of rock and the rerouting of oceans demonstrate that geography is the primary master of the global climate system. 34 million years ago, CO2 levels dropped past a critical tipping point. This triggered the explosive growth of continental ice sheets on Antarctica and shifted the Earth from a greenhouse state to an icehouse. In Europe, lush tropical jungles died out and were replaced by temperate woodlands and open plains, forcing a massive extinction of archaic mammals that were specialized for a soft, wet life. As the world became drier and lower in CO2, C4 grasses began to aggressively dominate the landscape, thriving while other ancient plants struggled. They used a specialized photosynthetic pathway to physically concentrate and hoard carbon dioxide inside their leaves. Eating these grasses introduced a survival challenge, grit. On windy, dusty plains, herbivores constantly ingested environmental sand and dirt along with their food. This drove the evolution of tall, self-renewing teeth in horses and other grazers to withstand a lifetime of mechanical abrasion. The cooling planet forced life to become tougher. Ruminants evolved complex internal fermentation tanks to digest fibrous forage, and herbivores developed specialized anatomy just to extract calories from a harsher, grittier landscape. 3 million years ago, the Central American Seaway closed, forming the Isthmus of Panama, blocking the flow of water between the Atlantic and Pacific Oceans. This closure forced warm tropical water to deflect north through the Gulf Stream. This change in circulation brought immense amounts of moisture to the high northern latitudes. The moisture provided the fuel for heavy snows. As the snow accumulated, it triggered an albedo feedback loop, where the white surface reflected sunlight back into space, cooling the region and helping to build the massive northern ice sheets. The resulting disruption to marine currents is linked to the extinction of ancient predators like megalodon. This cleared the way for modern, cold-adapted whales to flourish in the newly established, nutrient-rich currents of the cooling oceans. The closure of a single tropical gateway contributed to a climate feedback loop, providing moisture necessary for the ice ages that define our modern world. We now live in the Quaternary period, a time where the climate pulses between deep freezes and rapid thaws. This metronome is dictated by the Milankovitch cycles, subtle wobbles in the Earth's orbit and tilt. The variability selection hypothesis suggests that the rise of upright hominins was a response to this instability. Rather than evolving for one specific environment, early humans developed massive brains and tool use to survive a world that was constantly breaking and changing. We became specialists in handling climate chaos. Our intelligence developed as a survival strategy within the context of a fluctuating icehouse climate. Modern civilization is built upon the temporary stability of an interglacial pause. We rely on a climate that has, for a few thousand years, stopped its violent swinging. But we are currently releasing carbon at a rate comparable to the PETM warming event. We are pushing the atmosphere back toward a greenhouse state at a speed the biosphere has rarely seen. This brings us to the concept of hysteresis, that once a climate system is pushed past a chemical threshold, it can flip into a new state that is incredibly difficult to reverse. The 66 million year cascade shows that the biosphere always finds a way to adapt to a new normal. The question is whether our capacity for solving survival problems will be enough to navigate the cascade we have triggered.